Thanks for coming out tonight. Backwoods Bistro has great food, great drink, and questionable entertainment. So I'm glad you're here to hear my talk. I titled it Boot Camp for Metals That Make the Cut in High Field Magnets. And as he said, I'm a research associate at the MagLab. I'm actually a mechanical engineer that runs a materials testing department. And I've been there since 1993, so I'm coming up on a 25-year anniversary. And it's been a great place to work. It's, you know, a real boon to Tallahassee to have the Magnet Lab. And I'll, without further ado, get going here. We need a few good materials. The strength of the materials used in magnets is a limiting factor in the attainment of ever higher fields. So, researchers that use our magnets always want us to go to higher fields. And that's good for me since I'm a materials research engineer. So, working in high field magnets is not a job for run-of-the-mill materials. The candidates have to be strong and fatigue resistant. They have to work in high stress environments, be able to manage strain. There will be extreme temperature swings, dangerous electrical scenarios, and user demands and expectations. So users come here and they need our magnets to work while they're here. They spend lots of money to travel here. They have experiments ready to run in them. And we can't have them breaking down. So a lot of this is about the reliability of the materials that we use to build the magnets. The job requirements of those materials depends on which branch of magnet service they were enlisted for. So there's two main branches, resistive magnets and superconducting magnets. And underneath that, there's another breakout of pulsed magnets, powered magnets, LTS, which stands for low temperature superconducting magnets, and HTS, which is high temperature superconducting. And then every once in a while we stick two of them together and we call it a hybrid magnet. So it's part resistive, part superconducting. The main difference as far as materials are concerned is the operating temperature and the environment. So resistive magnets, the pulsed magnets, are cooled with liquid nitrogen before they're turned on, and they, during a short, like 10 millisecond long pulse, they warm up to almost boiling. We always use Kelvin for our temperature scale, which is equivalent, the same increment is equivalent to C. And so I got all the temperatures there in K, C, and F. And as you see, 77K is pretty dang cold. It's negative 321 F. Powered magnets are cooled with chilled water. So they operate from just slightly above freezing to just below boiling. Superconducting magnets are cryogenically cooled, and they run right at around 4 degrees Kelvin, which is almost absolute zero, minus 453 F. And even though one of these types of superconductors is called HTS, high temperature superconductor, by high temperature they're talking about like 80 degrees Kelvin or something. And that type of superconductor just barely works at 80 Kelvin. It needs to be cooled down to 4 Kelvin to have a lot of margin of safety in its operation. So boot camps for metal is just one way to describe the qualification testing of the materials that we use to build our magnets. One of my coworkers calls our lab the torture chamber for materials. So first I'll tell you a little bit, this is my outline. First I'll tell you a little bit about high field environment, why it's so demanding for these materials. I'll introduce you to a few different types of high field solenoid electromagnets. That's what we build. We build high field solenoid electromagnets. And then the very small number of exotic materials that we have available to be able to build these magnets. I'll explain a few engineering terms used to quantify the performance of materials such as stress, strain, tensile properties, fatigue, resistance, and superconducting critical current. And then I'll talk about the types of tests we perform, go into detail about 2 or 3 of these tests, tensile test, fatigue test, and critical current are the ones I'll cover a little bit more in detail. And it's a really unique situation we have here where researchers need higher field magnets to do fundamental research, and that's a catalyst for us to have to do cutting edge magnet materials research and development. So high field solenoid magnets are built at the MagLab by the Magnet Science and Technology group, which I'm a part of, also with tons of support from the other groups around the lab. This is a unique group, about 40 scientists, engineers, magnet designers, and students. And this apparently doesn't exist at other magnet labs in the world. They'll have to like kind of piece together stuff when they're, and there are about 10 other high field magnet labs around the world. What is a solenoid electromagnet? Well, one of the latest ones, it's Project X, I'm not supposed to tell anyone about, we're working on. This is an electromagnet. So our magnets are exactly like this without the nail in the middle, and where the nail goes, we call it the bore. And that's what the researchers want, this high-priced real estate that is the bore of the magnet. A junkyard magnet generates about a 1 Tesla magnetic field. And then the MRI scanning magnets are about 1 to 2 Tesla. So these are both solenoid type magnets. And solenoid magnets are used for lots of other things, like the starter in your car has a solenoid, or any switch that you electrically activate has a solenoid. And really what happens is there's a spring, like if that guy had a spring at his feet and he was non-magnetic, when we turn the magnet on, he would go zipping out or something like that and flick a switch. So electricity and magnetism are related. When electricity flows through a conductor, it generates a magnetic field. That's supposed to be a wire up above there, showing that there's a circular magnetic field produced. So when we wind the wire into a coil and charge it, it produces magnetic field lines similar to a bar magnet. This is like kind of better graphic for that, thanks to somebody on the internet. And so there's all these circular magnetic fields around the wire, but they basically are additive in the bore of the magnet. And the limiting, so I can't read what I wrote up there. Oh, I can read it here. The strength of the materials. Oh, I want to explain why the strength of materials is the limiting factor in getting higher magnetic fields. Lorentz force is a pressure between the magnetic field lines, which is much like north-south pole repulsion in a bar magnet. So the magnetic field exerts a force on the conductor. The conductor tries to move away from the bore of the magnet, creating a tensile stress in the conductor. The Lorentz force increases as the square of the field. So that means, like if I had 2 bar magnets and I had them on a table and they had 1 Tesla field and I was trying to push the north and south pole together and it took me 10 pounds worth of force to push it together, and then I increase that magnetic field to 2 Tesla, it's going to go up as the square of that field. So it's not just going to double like the field did, it's going to go up squared. So it's anytime these users want us to have higher magnetic fields, they're asking for a lot. Pulsed magnets. Is there any way we can get it to come down a little or no? Oh, okay. So what it says on top is pulsed magnets. Pulsed magnets have fields up to 100 T at our pulse facility in Los Alamos, New Mexico. They're resistive, normal conductor magnets. And they have this list of exotic materials that we make them out of. I won't bore you reading them, but we throw around these names of these metals and materials all the time. Xylon, graphite epoxy, MP35N, copper niobium, copper silver. It's a real common terminology for us. This is what the wire looks like that we make pulse magnets out of. It's a rectangular conductor. That's a payout spool. We wind the magnets here at the Magnet Lab and send them out to Los Alamos for them to use them. But we have to test the stuff here. So this is in my lab, and that's not me, that's another guy. Anyone in our lab's required to have a ponytail. So we take that wire and we machine test specimens. They're laying on the table there. There's some of them, those are tensile tests, some are fatigue, some are electrical resistivity specimens. Resistive magnets are the water-cooled ones that operate. They're steady state. So the pulse magnet only operates for about 10 milliseconds, and somehow researchers are able to get their research done in 10 milliseconds. I don't know how they do it. It would take me a lot longer. But these magnets are steady state, so you can turn on the magnetic field and leave it on, but they got to be water cooled because they're resistive. So they're like heating, ohmic heating, like your toaster would. So we flush them with water, and those pipes, that's the containment vessel right there for the conductor. The solenoid magnet goes inside of there, but we just blast ultra cool water through there and keep the magnet cold while it's being operated. This also uses very similar materials to the pulse magnets. And also, this is what the conductors look like. They're sheet metal rather than that rectangular wire. The exotic materials I'm talking about are inside the magnet. They're the conductor. They're the solenoid. So this is a technician stacking a bunch of those sheet metal discs. They're made with exotic materials. A lot of them, we call them micro composites. They're not an alloy, like they're copper silver would be one of them. And copper silver is basically part copper, part silver. It's not like an alloy, they're actually mixed together. And so these are composites, and they're especially made for us. We specify very high strengths, very low electrical conductivity, and we buy it mostly from Japan. Nobody in the US wants to do this for us. So we buy sheet metal like in the box right there at the bottom, and we send it out to a shop and get these perforations put in it for the water cooling holes. This is just an example of a bunch of different coils. Like we actually name them A, B, C, D, E. I don't know who came up with that terminology. Scott, was that you? So they, the highest field, the highest forces are at the center of the bore. So that A coil material is the strongest stuff you can get, but it also has higher electrical resistivity, and so it heats up more. So it anything you do to copper to make it stronger makes it more resistive, it makes it more sensitive to heating when you're flowing electricity through it. But these composites are better because now we have two materials together that are both very good electrical conductors, copper and silver, and they don't, it's sort of like they won't mesh mechanically, so they make the actual sheet stronger because they don't want to coordinate and work together. So they make it very strain resistant, but it still has high electrical conductivity. And nobody else in the world needs that. So we pay something like $350 a pound to buy that copper silver metal from Japan. And regular copper costs more like $15 a pound. And that's just to get it in this box in the sheet metal form. We still have to send it out and get it all machined. And so the magnets are very expensive, and that's another reason why materials testing is super important. So this is superconducting magnets, and on the left there's one that's called the series connected hybrid. This is a new magnet that came online this year, and it's a very good magnet that's both, it's got a resistive, a DC powered magnet at the center, but it has a superconducting coil on the outside of it the superconducting part's cryogenically cooled, and it uses a special superconductor called niobium-3 tin. On the right-hand side, this is an HTS insert coil. It's made with a material called Bisco 2223. And this is a tape material. I'll talk more about it in a little while. But this is a magnet that we're actually compressing in our laboratory to get it to make sure that it's the proper dimensions. Okay, so more about superconducting magnet materials. We use a lot of austenitic stainless steel. So your regular stainless steel, like that are 304 and 316, are very common stainless steels. Like the your sink at home would be 304 stainless steel or 316. That's an austenitic stainless steel, but it's not good enough for us to use in the magnets because we cryogenically cool it and it's expected to resist a lot of force. So we have this special alloy 316 stainless steel. And then the other two, JK2LB, Nitronic 50, are also special alloys. And HTS materials, they use these superconducting compounds, and we refer to them by their chemical name. So YBCO stands for yttrium, barium, copper oxide, and Bi2212 is Bisco, strontium, calcium, something, I don't know what, bismuth, strontium, calcium, copper oxide. So the 2212 is the ratio of the components in it. So austenitic stainless steel, like I just said, it's a specific type of stainless steel. Most stuff is made with carbon steel, like your car fenders, bumpers, almost anything that's regular steel, carbon steel is magnetic. We can't use that. It's and it's also, pretty amazing. Carbon steel is mostly just iron. It's 98 to 99% iron usually. And even a highly alloyed carbon steel called 4340, which also is called chrome moly by people that are like hot rodders or something, that's about 95% iron. But the stainless steels are much more alloyed. They have chromium, nickel, and other elements to, basically they were designed for corrosion resistance, but some of these elements are very good for magnet applications. Then this is just like a family tree for stainless steel. It all started with 304, and then they decided to alloy it to have different applications. So as you can see, it can get quite complicated. But our materials aren't even on this tree. They're like the next branches out because we took regular grades that were commercially available and then had to modify them further to make them work in our magnets. And then this just shows 3 of those, like a pie chart of their compositions. And when we order the metal, we specify these elements. So they have to do, at the mill, they have to do chemical composition analysis. So basically, one way at a steel mill, they'll have an ingot or a melting pot full of metal, and they do an ingot analysis, and they make sure they get the mix right. So they got to have so much chrome, so much nickel, moly, all those things. But we tell them exactly how much to have, and when they send it to us, we actually double check that and make sure that they nailed the chemistry, because it'll have a bad result. If it doesn't have the exact chemistry that we want, it won't end up having the strength and the fatigue life, and also it'll have some other fracture problems. So we look at the microstructure of the metals, and up above is lower magnification views of these 3 metals, their grain sizes. So we have very good metallography and microscopy labs at our work, and we're able to really investigate the microstructure of the metal and see the arrows are pointing to what we call inclusions. These are like impurity elements that were floating around in the mix, and they end up in the grains. So they can cause problems. Like if we test the metal, and it turns out to be very brittle. And we look at it here, we see that basically they didn't heat treat it right, or they didn't mix the chemistry right, and so we'll trace why there was a problem with it. This is just some example of the types of products that we get. These tubes are called conduit, and what we do is put superconducting cable in the conduit, and the conduit is what resists the Lorentz force that I was telling you about. All right, now I want to talk a little bit about 3 different types of tests. Tensile test, cyclic fatigue test, and a critical current versus strain test. So, tensile test is basically the most common simple material strength test. It produces a wealth of information about material strength, and it's a standardized test with, it has an ASTM specified method, like a cookbook tells you how to do it. So you basically take a piece of metal, a sample of your metal, and you machine it into an acceptable test specimen, put it in your machine. We hook a device called an extensometer, or in this picture it shows it as a strain gauge, that will monitor the length change of the metal while we pull on it. And then it's grabbed by some grips, and we have hydraulic or screw-driven machines that can pull the piece of metal apart. And then we generate this data here that I'll talk about on the next few slides. This is a picture of our machine, one of our machines. This is a 10-ton capacity machine. So it can push or pull 10 tons of force on the sample. We want to be able to do that with the sample at cryogenic temperature, so we designed a frame, and we have a vacuum insulated thermos that we can put around it and fill it up with liquid nitrogen or liquid helium, and we can do the tensile test at the temperature that the magnet operates at. This is the first time I had a talk with beer. Oh wait, last night I was talking to my beer. No. So this machine has a whole bunch of specifications. We have 4 of these, and they're pretty much non-stop in use. This is a kind of close-up of the tensile specimen on the left. So it's a round bar. We machined this out of, a chunk of metal, and it has threaded ends like a bolt, but it has a nice smooth section. Like if we just had it be all threads, it would break sooner because of what's called a stress concentration. The threads are concentrating the stress. We need it to be a uniform cross-section. And then those things that are in the picture there are clip-on extensometers. They monitor the extension while we pull on it. And they monitor it down to like unbelievable dimensional quality of a micron, plus or minus 1 micron, which is 1 times 10 to minus 6 meters. And for example, a human hair is about 80 microns. So, we could easily measure, we can measure hair, and we have to sometimes. We measure like threads, carbon nanotubes, and things like that. So a little bit more about test. Like I said, it gives you a bunch of information. It tells you the yield strength, the tensile strength, Young's modulus, Poisson's ratio, elongation, reduction area, and strain hardening rate. So this is a graph of the results of the test, and what we plot is stress versus strain. Let me see. I want to go to the next one here. See if I forgot anything. Oh, there's some examples of some specimens that were broken. And so this is the procedure I got up there where you can't see. It says tensile test procedure. Measure the specimen's cross-sectional area. So if it was round, you measure the diameter of it in the reduced section. Scribe some initial gauge marks. So we actually scratch it with 1-inch marks. And then install it in the specimen and in the machine, attach the extensometers. Then you run the test in displacement control. You just start, this machine is heavy duty. It just starts moving up, pulling on the specimen at a constant rate. We record the force and the displacement or the extension of the specimen. Then the data is acquired into a Excel spreadsheet, and we change force and extension into stress and strain. There's going to be a test on this after, by the way. Stress equals force divided by area. So stress is just like pressure. It's pounds per square inch or newtons per millimeter squared. And by the way, newtons per millimeter squared are megapascals, which we really use megapascals or pascals for pressure and stress. We don't ever talk in pounds per inch squared. And then strain is just like a percent change in length. It's the amount of it changed divided by the original length. So if we plot stress versus strain, it looks like this. And as you can see on that graph, if you can read the y-axis, at about 300 megapascals, you can see the sample starts giving up. It's yielding. So by the time we get to 400 megapascals, it's a lot longer than it was when, before 300. Up to 300, the relationship between the force and the elongation of the piece were linear, and then it becomes nonlinear or it yielded. So I have the results of this test written here. It says the yield strength was 382. So that's where this dotted line crosses the curve. That's in order to give us a little leeway and sort of trying to say, it looks like it yielded at 300. And then, another lab might test it and say, no, it yielded at 320. And another one might say, 200 or something. So we got to give some leeway. So we do a 0.2% offset. So that's yield strength. It's an important number. Like you can design now, if you know the metal's yield strength, you only want to go to about 2/3 of that in your design. So you'll make sure that the parts in your metal only see about 200 or 250 megapascal. And then the ultimate tensile strength is what it breaks at. So that's just the total force divided by the original area. And this case, it was 540 megapascals. So this curve goes on. I didn't show it, but it goes way up to 540. And then elongation. So after the sample breaks, we push it back together, and then we measure that original 1-inch scribe marks. And so now if it's 1.1 inch, that means it elongated 10%. And that's super important, because if your metal, like a lot of our metals, we require they elongate 20%, or we can't use them in our magnets. Okay, now on to another test, IC versus strain. So this is a test of the high temperature superconducting metals. So there's basically 3 types of these: YBCO, 2212, 2223. The HTS compound is very delicate and brittle and difficult to use. And if you could see the drawing up above, basically it's applied onto a high strength strip of steel because it has no strength. So this to me is analogous to like spray painting a very thin layer of spray paint on a steel tape. Now the spray paint or the thin layer of paint is what carries the current in our material, and the steel is what carries the load. So that current is trying to get away from the magnetic field, but it's butted up to the steel, so it can't move. But we do a test where we pull on the steel until we start cracking that brittle superconducting compound. And you see 2 little wires, they're detecting when that compound starts to crack. This is a graph of how that happens. So we're doing a tensile test, but we're flowing electrical current through the sample. Current is on the y-axis on the right-hand side. And as you can see, that little thin piece of tape, it's really 0.1 millimeters thick, was carrying 180 amps of current when there was no strain on it. As we pulled, those dots are the current. So after the material yielded, the current went to hell. It couldn't like basically the spray paint on that tape started cracking and the current can't travel through it anymore, and so its resistance goes way up and it's not usable anymore. So this test allows us to determine how far you can push this tape in a magnet before it's going to start crapping out. Okay, fatigue. Very important. You know, most people are used to this something called fully reverse cycle fatigue. Rotating machinery is like basically propellers, windmills, you know, pulleys. They're all stressing things in a what's called a reverse cycle. So that little diagram shows if you just hung a piece of metal out and hung a weight on it and turned the motor on, that metal is going to be cycling, tensile compressive. I mean, it's bending basically, but it keeps rotating. And so it sees a cyclic stress in a sine wave form that's shown right here up there. Well, we could hang different weights on it, and we can wait until it breaks, and we can count how many cycles it took. So the graph we plot is the stress versus the number of cycles to failure. And usually we have to plot the cycles to failure on a log plot. And so in this case, you can see that this metal, we would need the stress to be down under 500 megapascals to make sure it could last forever. Of course, they don't ever do that for car design. They jack it way up, make your car break, and I don't know why, but because it costs more. So we don't really do rotating machinery tests. We do what's called tension because our conductors don't rotate. They're just getting tensile stress, and then when you turn the magnet off, they go back to zero. So they look like this graph on the bottom, the stress for them. This is an example of a part I didn't want to break. So this is a pull rod in one of my machines, and it fatigued and it broke. But I had used it for many tests, so it had lots of cycles on it, but obviously I was above the limit that would have made it last infinitely. And fatigue happens in 3 stages. There's something called crack initiation. So, like I said before, threads are stress concentrators. And you know, if you ever have seen a broken part on a lawnmower, bicycle, whatever, it always breaks right where the thread stops or whatever. So right where that nut used to be on the thread, the very first free thread had a stress concentrator. It initiated a crack, then it grew in that light zone, and then the dark zone is where it just broke catastrophically. So one of our alloys that we use for our magnets called JK2LB, we run these tests and we run them at different stresses until they break. And we generate this data. So there's a lot of scatter on the data, and we plot it on the it's called the SN curve, stress versus cycles to failure. And then one way would be to bracket it with error bars, and this is called plus or minus 2 standard deviations. And then we could say, well, it looks like if we want to go, this is 1,000,000 cycles. 1 times 10 to the 6th is 1,000,000. If we want our magnet to last 1,000,000 cycles, we better have the stress down below around 500 or 400. But if you're not designing for fatigue, like if you have something that you know is not going to fatigue, like basically a part in your house that's just holding up something, you do static design, it's called, and you design to 2/3 of the yield stress. So that metal, 2/3 of the yield stress, or 1/2 of its tensile strength, are those 2 dashed lines. And this is just to show you that it would break if it was in a fatigue case, but if it's in a static case, it doesn't get any cycles on it. So it's just weird. You're below the yield strength of the metal, but you can't see what's going on, but just because it's cycling, it's eventually going to break. And actually, we don't even use the 2 standard deviation. We use something called ASME boiler pressure vessel code, which makes us put a factor of safety of 2 on that data. So all that scattered data was curve fit, and then we reduced it by a factor of 2. And so now you can see we can only use this material at 400 megapascals if we want it to last 1,000,000 cycles. And really, you know, most likely we could use it at 500 and last 1,000,000. But when the magnet costs $12 million, it's going to be too much to risk. And you might say, well, why don't we just over-design it? But I just told you copper costs $135 a pound, or was it 350? What did I say? Scott gave me that number today. But so we can't over-design. We can't just double the dimensions of things because every material we use is an exotic material only made for us. It's not like they're making it for jet engines and we can just glom on and get some for us. We got to like special order it. We have lots of microscope capabilities, as I said before, and we'll look at the tensile fracture surfaces, and you can learn a lot about the metal. So in this picture, it says crack growth. That's where the fatigue crack was going, and then it overloaded and broke. This is a good-looking fracture surface because it has a bunch of looks like craters. If the fracture surface looks like facets and it's brittle, that's bad. And you can see there's a little bit of that up here on the right. Also, you can see what's called striations. So those are actually fatigue crack growth cycles. So each one of those, like counting rings on a tree, that's one cycle, and the crack advanced across that grain. And what you're really seeing are different grains in the metal. So the fracture went across the grain, but it moved one little increment at a time. And our scale bar down here says 10 microns. So that's about 1 micron. And before I told you hair is about 80 microns. So the crack is growing very slowly. And then just some more fracture analysis, this is called. And we can find basically what's called inclusions or impurity elements in the pit of the craters. And, you know, it's got to break somewhere. So they can't make it perfect. But if they had messed up and these were big, the material wouldn't last it as long as we want, and we can tell them, you did something wrong, or we'll reject the material. And then I want to, I'm coming close to the end here. I don't know how much time I spent, but there's one big program we've been working on for a huge fusion reactor that's being built in France. And this is a international collaboration between something like 23 countries. And a fusion reactor is a clean way to produce energy for the future. But I've been working on it for my 30 years of my career so far, and they haven't built one yet. I mean, we're building one. It's supposed to get turned on in 2020, but they always keep it out about 5 years from whatever the date is of now that they're going to turn it on. But hopefully it will get turned on in the 2020s, and this is going to be a clean way to produce energy. This one's a demonstration reactor, and it's so they have tons of superconducting magnets in this, and there's a stack of solenoid magnets that are in the middle of the reactor, and there's a guy up there for scale to show you how big these magnets are. And the conduit that has to react to Lorentz force also has places where they need to put plumbing ports on it. So they're boring a hole in the side of the conduit and putting a port to be able to pump liquid helium into there to cool it down to cryogenic temperatures. Well, that causes a stress concentrator, and so they needed us to test it. And since we have the expertise and the infrastructure, and like I told you, this magnet design group that's unique around the world, people come to us to do stuff like this because we have the machines and the know-how. So we designed this test specimen, and then we ran the test. And this is pretty cool. The test specimen's over there on the left. We had to put 2 of the helium ports in it to keep it symmetrical, because when we pull on that, it would have bent in one direction if you only had a hole on one side. And plus you get 2 tests for the price of 1. But we had to fatigue this thing between the loads of 607 kilonewtons, which is 61 tons. So we had to pull 61 tons of force on this and then let up and then pull it, and it had to survive that 540,000 times. Well, here's the test setup. So we have a big machine, big hydraulic machine. We designed a fixture. We put the sample down in liquid nitrogen and ran the test, and voila, it broke at, this one broke at 535,000 cycles. Can you believe it? It's supposed to go 540,000. It was 5,000 cycles short. And we had to test 6 of them. 2 of them broke early, and a couple other ones survived, but now they're backtracking, trying to figure out what they can do to improve their design of this part. And I want to show a little movie of that test that's sort of sci-fi looking, if it'll work. So this is just us opening up the tank after the specimen broke. So there's a stainless steel tube that was around the specimen, and the thing was all in liquid nitrogen, and so we're just trying to get it out of there to see where it broke. We never know. Like one test, that threaded pull rod I showed you broke, so it's always a mystery. You can't ever see what you're doing when you're doing tests at cryogenic temperatures. They're always down in vacuum insulated tanks like this. And I had one more little thing I wanted to show, which I don't know if this will work. This is my feeble attempt to show how Lorentz forces are generated, or what it does to the coil. So as you power up the magnet, the coil actually gets shorter and wider, fatter, and so the wire is getting stressed. That's all that was. But other than that, that's all I have. Thank you.